Yeah, thanks everyone for joining us on the latest episode of Golang Live. Prez is a senior Golang engineer who's going to give us a talk this evening about thread safety in Go. During the presentation, he'll obviously open it up for question and answers, so feel free to obviously in the chat section provide questions as we're going through, and they'll be asked during certain parts of the talk. So I'll just let Prez sort of kick off the presentation, if that makes sense.
Yeah, sure. Let's go ahead.
Perfect.
Be able to see my browser or something.
Yeah.
That's nice. Press. Awesome. Right. Now you might be hearing my cat's meows occasionally. It's about time he eats. So he might be a bit nervous, but apologies for that. Hopefully he won't be too troublesome. Well, welcome everyone. First, thank you everyone for joining today. I'm really excited to have you, and I'm really excited to be talking about a topic which is very close to my heart, very interesting, which is thread safety. In particular, we're going to be talking about thread safety in Golang. But if you happen to be coming from a different background, such as Java or C# or whatever, I'm certain this will be valuable to you too, because the principles and concepts we're going to discuss are more or less applicable in most languages. Now, let's get started. So, as Shaun introduced me, I work as a senior Go engineer at BottlePay, and I was previously at Uber. My name is Preslav Mihaylov. I'm based in Sofia, that's in Bulgaria, working from my cozy home. And I do all sorts of talks like this one and various courses, some of them online, some of them on site. And I also maintain this Twitter profile. If you are a Twitter, user and you like following it, if you like going on Twitter, you can follow me there for various tips and tricks related to Golang and whatnot. I mean, I tweet about all sorts of things. But in general, if you don't have a Twitter, I really suggest you create one. Not necessarily to follow me, but because tech Twitter is actually a really valuable place. You can learn a lot as an engineer. I mean, if you have Facebook and things like that, just ditch those and go on Twitter. It's much better. All right, so this talk will be a bit interactive. First, you can obviously ask me questions all the time, and I'll monitor the chat occasionally for questions at various milestones throughout the talk, but also I'll take the opportunity to ask you questions as well. In order to do that, I'll ask you to just scan this QR code or open slido.com on your mobile phone and enter the hashtag thread safety event. In there, I'll have just a simple question, which I'll just re-ask all the time related to the talk. You see what it is. In order to save time, I just ask you to do this now rather than doing it later. Now, to get started, first, are there any questions so far? Quickly check. No, nothing in the chat pops up. So
we're all good for now. Yeah.
Awesome. Right. So first off, this is called thread safety in Go rather than concurrency in Go. This is for a reason, and the reason is that well, concurrency is a popular topic, especially in Golang, because it's known for its concurrency mechanisms and concepts. But there is, despite all that, there is this lack of understanding about a particular subject which is part of concurrency, and that is thread safety. That comes because in Go you have this thing called channels, which is really cool. It allows you to not communicate by sharing memory, but sharing memory to communicate, or was it the other way around? Anyways, I tweeted that today. So you can check it out. But anyways, channels are just the main mechanism to tackle threat safety in Golang. But I believe it's not sufficient. There are cases where channels are not enough to, make a working and resilient web application. And that's where other mechanisms come into play. Apart from that, most courses, books, materials, tutorials which are out there, they're insufficient because they cover how you create Go routines, how you use channels to communicate among them, but it doesn't cover everything you need to know about threat safety. So that's the reason I'm making this talk, because there isn't enough love for threat safety, and I want to bridge that gap. And if you think you don't need this, well, unfortunately, as I'm using this analogy here, if you try to write concurrent code without understanding threat safety, you might you might run into some serious issues which will, get you in trouble. And yeah, it's good to know how to deal with those. So what are we gonna focus on? We're gonna focus on learning the fundamentals of this. It's not an easy topic to tackle, so won't be able to cover everything in 50 minutes. But we will cover enough for you to be, to be able to go back to your job and be able to use the stuff we'll cover to a good degree to, write productive code. But also I'll provide some guidance on where to go from there. Right? The agenda is what trade safety even is, whether we should care about that. All hint you should, obviously, if I'm making this talk. We'll discuss afterwards. Comes the main main dish for the night, actually understanding the various use cases where we have to deal with threat safety and how to address various issues which come up. And finally, as I promised, I'll cover where to go from here after this talk. Right, so I see this red banner in my chat thingy. So I see that Dimitri said share memory by communicating. Awesome, thanks for correcting me on that. Okay, now let's get started. What does threat safety even mean? Well, let's start with defining what the safe class is. So imagine you write some class and you ship it to production. In which cases it's safe and in which case it isn't. In the usual scenario, it is safe whenever it behaves the way it has to. If there aren't any bugs, if it covers all the cases it has to cover, and etc. But basically, it does what the class is meant to do, and it does it in a good way. Threat safe classes, on the other hand, have the same property, but the difference is that they're able to sustain that property even when they're bombarded by a gazillion Go routines, and they're under pressure all the time. Because you'll see later on in this talk that there are cases where you have safe classes, which if you use in your regular Go programs, in most cases they will work well. But once you start using those structures or packages or whatnot, inside Go routines, you might run into trouble you didn't anticipate. Okay, so should we even bother discussing threat safety at all? Well, one thing I have encountered when I'm talking about this topic is that usually we have some web developers which come to me and said, hey, threat safety is a cool topic. It's interesting and all. But I really don't need it because I'm a web developer. I just write CRUD applications. I don't really use threads in my code base. As long as I don't spawn any new threads, which I really don't, I mean, I'm fine, right? I can just go ahead and be happy with myself. Unfortunately, that's not sufficient, actually. Even if you aren't spawning threads or coroutines in your code base, you still have to consider thread safety. You can still run into issues. And no, I'm not saying this because I want to, make you think the topic I'm discussing is a very important one. I'm actually saying it because you can indeed run into trouble, because if you are a web developer, or most developers nowadays are already writing multi-threaded applications, especially if you're a backend developer, and channels cannot save you every time. Consider this consider this small program. It's obviously, you can't run it just by itself, but it's a snippet of a program, and it's meant to be a very simple chat where you can get the messages for a given user, and the messages are an array of strings, and you can send a message to a particular user. That's it. That's all it needs to do. And obviously I've oversimplified it a lot for the sake of the example. But although this program is nice and sweet, it already has a lot of issues. Too bad I already spoiled this for you. I was about to ask whether you think it's safe or not. I spoiled it for you, so I'm not going to go into asking you, is it thread safe? But that's something we'll be asking ahead in the talk, so be prepared. I won't spoil the answer next time. Anyways, why is this class, well, it's not a class, it's a program, mini program. Why is this program not safe? The reason is that we have this map here. And this map we're accessing from get messages and send message. Obviously, you don't see any coroutines found in here, which modify this map concurrently. However, just because you're not spawning coroutines doesn't mean your functions are not executed inside coroutines. And in fact, that's exactly what happens, because usually when you have HTTP handlers or any kind of web handler for that, in fact, most requests are handled in different coroutines. Sometimes these coroutines might not collide and all, but most of the times you can run into issues, because imagine you have 500 requests at a time. The way the server executes your requests are not, okay, I execute one request and until it's finished I start executing the other. No, it actually starts executing them all at once, or at least let's say 100 at once or something like that. And when that happens, what can go wrong is that when accessing this map, you can run into issues where certain messages might be missing, or something else might go wrong. And if you don't understand how this can happen right now, don't worry. By the end of the talk, you should be able to understand it. Okay. Any questions so far?
I think we're okay so far. If anyone has any questions throughout, feel free to ping them in the chat, and I'll ask Preslav throughout the presentation. But I think we're okay so far.
Thanks, Shaun. Okay, so that drives us to the second part of the presentation, discussing various cases where we have to think about thread safety and how to solve the various issues we encounter. First, the thing we have to understand before even looking at thread safety issues is understanding when potentially there might be such an issue. In order to understand that, we'll start with this very simple example where we have two functions. Both of the functions are returning a map of integer to string. Previously, in the example I showed you before, you also had a map which was accessed at the same time. Imagine in this case, these functions will be executed by many coroutines, like 1 million coroutines at a time. And the question is, which version of the function is thread safe and which version is not? And obviously, the difference between the two is that in one case, you don't have any thread safety mechanisms in place at all. In the other case, you have a sync.mutex. By the way, I think this should be without the star here. I probably got this wrong, but imagine there isn't a star there. Anyways, it still works. So in this case, you have a lock. In this case, you don't. And here we lock the function, and then we defer unlocking it, meaning that this will get executed after the function finishes, not at this line. Okay, so my question to you is it thread safe? Right. So feel free to join me at slido.com thread safety. I can't see if anyone's joined yet, so I'll just enable the poll and wait for your answers. I'll be happy if you can provide some opinion, even if you're not certain. Oh, wait, I didn't ask the question correctly. Like, is it thread safe? Because there are two functions, right? It's not just one. Okay, let's actually try this instead. Let's discuss only weekends unsafe. Let's say weekend safe is fine. Weekends unsafe, is it thread safe or not? So that's the question. You can change your answer if you already answered in Slido. Okay, so the split is 50-50 for now. And most are answering that it's not thread safe. Let's see what the comments are. So Andre says both are thread safe. Alex says, would you mind showing them again? Right. So, oh, sorry, my cat just sabotaged me right now. I'm not sure if you saw that. Was about to run over my keyboard. Right. So these are the functions. Okay, so obviously there is no consensus, and most people are clinging towards no. Although Živko and Andre are saying that both the functions are thread safe. All right, so what's the answer actually? Well, the answer is that weekends unsafe is thread safe, regardless of the fact that there is no lock whatsoever. And why is that? Well, Živko actually spoiled the reason for that because he wrote that there is no shared memory. And that's right on spot. When we are discussing thread safety issues, they can only occur when we have shared mutable state. What does that mean? Well, imagine that we have two threads and they have their stacks and they have their heap, which probably most of you have encountered these stuff. And these arrows here are some data they're pointing to, they have reference to. In this case, thread 1 has its stack and thread 2 has its stack, and this is non-shared state because everything which goes on the stack is just local to the thread which owns that stack. But once stuff get on the heap, then things get interesting because the heap is shared among multiple threads. However, as long as the state which is in the heap is only visible to one of the threads, like in this case, for example, thread 1 references this non-shared state number 1. When that happens, it's perfectly okay to consider that piece of code or that data as being thread safe. Because when a thread has visibility to some data, and when it's the only state, when it's the only thread which modifies that data, it's perfectly safe. There is no way to run into thread safety issues. The only case when there might be a potential thread safety issues is when we're accessing shared state. So if thread 1 points to, let's say, some map of int to string, which is not local for the function, but actually it's accessible by multiple functions which are executed in different Go routines, then you can have an issue. Then you have shared state, and then you have to consider how to address that. So in this case, weekend safe and weekends unsafe are both thread safe, because notice that the map here is created inside the function. This means that the map is only visible to inside this function and inside the thread or the Go routine which is executing that function. Therefore, there is no way to have thread safety issues. Even if the map itself doesn't have any mechanisms to prevent it, it's fine because there's only one thread which is ever going to access it. On the other hand, this first example I showed you, this is not the same, because here you have a map which is accessible by both functions. This is no longer a map which is local to a function. It's accessible by multiple functions which can get executed in different Go routines, and then you might run into trouble.
Right, so we've got a question from Annie. He just said, is weekends unsafe also thread safe when we have multiple Go routines accessing it?
Yeah. So good question, Annie. Yes, weekends unsafe is also thread safe, because despite the fact that multiple Go routines are accessing the function, every time a Go routine accesses that function, a new map will be created. Therefore, effectively, every Go routine will be working with its own map, which is not shared. Hence, you can't run into any issues. Okay, where were we? Okay. Awesome. So that's probably, the first big revelation for the night. Hopefully there are more to come. Now let's actually see, when you have issues, thread safety issues, how to deal with them. In this example, we have a structure called hit counter, which has a counter inside. And this hit counter has a hit and get function, and in hit it increments the counter, in get it just gets the counter. This is an example of a structure with functions attached to it, which is actually not thread safe. So this is different from before, because if we now have multiple Go routines which have access to the hit counter, and multiple Go routines are accessing hit or get at the same time, then you can run into issues because they will be dealing with the same data. In order to prevent that from happening, what you can do is you can use that lock, which I showed you. I have that mistake here again. Sync.mutex is non-pointer, so a non-pointer type, so you shouldn't use the star here. I should fix that later. Anyways, in order to prevent thread safety issues, you need to have a lock, which is of type sync.mutex, and every time you have some function which accesses shared data, in this case the counter, you need to lock it. What this will do effectively is that, let me actually use this opportunity to draw a bit. So I'm stopping the screen share just for a second to open OneNote where I draw stuff. However, I also keep some very confidential data and stuff. So I prefer you not, see those stuff. Okay, cool. Creating a new page here. Okay, so ready to screen share again. Oops, I shared the wrong desktop. Okay, so now I'm taking this function and pasting it here. So imagine that now we have several threads which access this. The first thread comes and enters hit. And the counter here, let's say CNT, is equal to 0. When the first thread enters counter, what will happen is it will first go to this line. Imagine now that at this point, a second thread comes and tries to access hit effectively at the same time. Since we have a lock, what this lock will do is it will prevent any other thread from accessing the piece of code which is between lock and unlock, in this case, the whole function. Due to that, this green thread will stop execution and wait until the red thread is finished. So it will just hold for now. Next, maybe another thread comes and it has to wait as well. So it holds, and then we go back to the red thread again. It continues execution and it increments the counter. So from 0, it becomes 1. It exits that function and we're good to go. This is no longer here. Next, either the green thread or the blue thread continue. So they enter the function because the lock is lifted now. One of them succeeds, goes to this line. Let's say it's the blue one. Let's say at this point, the green thread wakes up again. It tries to enter, it can't, because although the red thread is no longer there, the blue thread is now in its place. So again, it has to wait. The blue thread finishes incrementing the counter, it becomes 2 and it exits. Next, the green thread does its thing, and in the end, the counter becomes 3. Okay, so that's what happens when you lock a function and it's accessed by multiple threads. And what can go wrong in the other case? Well, what can go wrong is that if you run the non-thread safe example and you hit it 10,000 times by multiple threads, you might get this answer. So this is totally arbitrary, meaning that if you run it on your machine, you can get that answer. You might get lucky and get 10,000 instead, or you might get something totally different. The point is that when you have non-thread safe code, the result is non-predictable. You can't really predict what will happen. However, if the code is thread safe, then it's totally predictable and it will always be 10,000, no matter how many threads you use and how many times you execute the function. Okay, cool. In the other case, when we don't have come on, I want to use the arrow. So in the other case, when we don't have a lock, what will happen is that thread number 1 will go inside. This is an example scenario, obviously. Thread number 1 goes inside and executes this line. Now, how this operation works ++ is that effectively the thread first reads the value and then increments it. So if the value is equal to 0, thread number 6, let's say this is the value which thread number 6 reads, it will read the value 0. At that point, let's say the blue thread comes, and since there are no locks anymore there, it will also be able to enter this function while the red thing is doing its thing. So the blue thread will now go inside, and also it will read the current value, which is still 0, and then perhaps increment it to 1 and finish. Next, the red thread will resume execution, but it will not notice that the value has changed at all because it has already read 0 and it thinks the value is 0, so it will increment it from 0 to 1. And the effect is that instead of this counter being incremented twice, it will only be incremented once. And you can imagine if this happens 10,000 times, and on every time you have some risk of this bad scenario occurring, you might imagine that you have unpredictable results.
Right, okay, I think there's another question from Annie. I think it's what is Go routine in this example, and then I think there's some symbols involved.
Yeah, so Go routine. So a Go routine in Go is something like threads in any other language, and what it does is effectively a well, this is typically not included in the talk, but a Go routine or a thread is you can imagine that your CPU has several workers which are idle. So those are your cores, and each worker can execute some piece of code. Sometimes some of them are sleeping, but at other times all of them might be involved. And a thread is effectively a piece of work which gets executed by one of the workers, and it might only be one worker who's currently doing some work, but there might be multiple workers. If there are multiple, let's say there are 2, you might have 2 different pieces of code, or maybe the same piece of code, but being executed at the same time from 2 different workers, meaning that your program, your hit or get functions are executed in parallel by more than one worker. This is in a nutshell what a thread is, and obviously it's very oversimplified. You know, someone who knows, who is more knowledgeable might come and say, yeah, that's not exactly it, and you'd be right. But my point is just to give you a good idea to be able to understand the talk. When I'm saying Go routines or threads, I mean that your code is being executed simultaneously from different people, let's say, who are running your code at the same time. Okay, hopefully that makes sense. All right, cool. So, and that's the basic example of when you have non-thread safe code and how to deal with it. Okay, and using mutexes, that sync.mutex thingy is typically the standard way to deal with thread safety issues, other than using channels, which you might use in different scenarios. Okay, now we're getting to a bit more, well, it's not advanced, you see, it's quite simple, but another separate topic, which is delegating thread safety, which is my favorite thing. Imagine now having this knowledge in hand. You are tasked with creating a phone book, and a phone book has two functions, which are the ability to get a phone number by a name and setting a phone number by name. In order to achieve that, you need to store a map of string to string, and you have to, do the regular map operations to set and get values from it. Now, having passed through the first couple of slides, you know that you can use mutexes, and you should use mutexes here in order to protect the map from being accessed concurrently, accessed from multiple Go routines or threads, because if it is accessed in parallel, you might run into issues similar to the ones which I previously showed. However, this is fine, this code is fine, except for the asterisks, which I should remove again. But there is usually a better way to achieve the same thing, and that's leveraging someone else's work. And the way you can achieve that is by delegating thread safety to some kind of structure, some kind of package which achieves the thing you want, but also has thread safety on top of it. In this case, when you want to use a map of, let's say, string to string, instead of using the vanilla map you have in Go, you can use this nice little map called sync.map, which is coming from the standard library. And it has the exact same functionality, but it also guarantees you that every operation will be thread safe. Meaning that instead of dealing with thread safety yourself, you can just rely on the work someone else has done and just reuse it. In this case, notice that get phone number and set phone number has no locks. Using it feels like just normal non-thread safe code, but in fact, this is thread safe code, and everything is coming from the type you are using. So that's what delegating thread safety means. Instead of doing thread safety stuff yourself, just rely on the work of some package or some structure which already does it for you. This is the best way, in my opinion, to handle thread safety issues, because well, you just have less work to do, and usually the people who implement these structures and packages can do it a lot better than you. Okay. Alvin asks, so no need to lock and defer unlock anymore. Exactly, yeah. So since we are using sync.map over a vanilla map, we don't need to lock anymore, because sync.map out of the box has thread safety in it. Therefore, there is no way those two threads which come to access or mingle with the data in some bad way. Okay, Annie, is there any performance impact of using sync map versus a normal map? So that's a very, very good question, a bit advanced, but yes, there is a performance impact. And in fact, using sync.map when dealing with concurrent applications is faster and more efficient than using a vanilla map with a lock. So other than this code, other than this code being simpler, it's also more performant out of the box, because I hinted about this, but I told you, typically people who create those kinds of packages, they not only do the job they have to do, but they also put the extra effort to do it in a very, very efficient way, so that it will typically be even better than if you do it yourself. So yes, there is a performance impact, but for concurrent applications in particular, using sync.map is better now in terms of performance. Now for normal non-multi-threaded application, using sync.map is an overhead at the very least, because it's a bit more cumbersome to use. It uses the empty interface. It doesn't have types inside, so it's just trickier to use and can get you in trouble in terms of just writing the code, that is. Okay, will atomic operations be faster than the sync log mutex operation? Alvin asks that. Yes, atomic operations are typically faster than using logs. Due to the way they're implemented. This is something I'll mention in the end. I told you how to get some further guidance beyond this talk. I'll provide that, and in that guidance, I'll tell you how to learn about, for example, atomic, because it is an interesting topic. It's just really out of scope, because atomic is more performant than using log. The question is why, and that's something I'll leave to you to check out on your own. Okay. Now to recap, delegated thread safety means relying on the thread safetiness of the objects you use instead of doing it yourself. But also it means using third-party packages, meaning that when you write your web applications, many times you haven't known about thread safety at all, and yet you kind of write thread safe applications. And the reason is that typically the packages you use in your web applications are already thread safe. For example, if you're using some database access packages and you use them from multiple threads, typically they are thread safe, so you're okay. But there are cases where you still have to consider this, mostly when you have some shared memory for trickier stuff. Okay, now next up, atomic compound actions. So imagine that we want to extend this a bit. The class or the structure has done particularly well. You know, the boss is happy and they want to add a new feature. The new feature is that whenever you set a new phone number, you will first check if one exists already. And if it doesn't, only then will you store the phone you are given. Okay. In this case, I want to ask really quick, is this thread safe? In order to do that, I'll stop the poll, I will reset the results and start it again. Okay, so go ahead, let's vote again. We have our sync.map. We use it in our phone book example. In one case, we just get the number. In the other case, we have this if statement where we first check whether a name exists, and only if it does, only then we store it. Question is this functionality thread safe or not? Okay, so many people answered no, it's not thread safe. Some people are voting for yes. Let's see if someone will spoil stuff in the chat. Not for now, so this is an interesting debate. Okay, so 9 people voted already. I think that it's sufficient for now, so I'll stop the poll. And more people voted yes, but there were some who voted that it's not thread safe. Wait, sorry, more people voted that it's not thread safe. Some voted that it is. And the correct answer is that this is not thread safe. Despite the fact that we're using a thread safe collection, which I told you is pretty cool and nice to use, this code is not thread safe. And obviously you might hate me right now, you know, think something like, why did you lie to us? I mean, you just said a minute ago that this was fine to use. Suddenly you're saying it isn't. The reason it isn't thread safe is because although it is thread safe for the individual operations it supports, whenever you have compound actions, then you might run into thread safety issues again. And which is the compound action in this case? Well, it's this one, because we have two steps. We have checking whether the name exists and then storing it. So what can go wrong if we do that? Pointer again. Okay, so what can go wrong? Well, imagine again, our first thread comes, our second thread comes. The first thread, passes this check and the name doesn't exist yet. So it at this point, the second thread comes and tries to do the same thing, but it's stopped. Imagine there's a lock in there. The second thread is stopped, so it can't do the check. Therefore, it waits. The red thread continues and goes to this line. But just before executing that line, the green thread wakes up. And before the phone has been set, it does the check again. And this time, since the red thread hasn't finished yet and the lock is released, it checks that the name indeed doesn't exist yet. So therefore, the green thread gets to this line as well. And at this point, it doesn't matter which thread goes first. But what effectively happens is, imagine we have some K and we have to store phone 1 and phone 2. What will happen is that the first thread will set the value to P1, it will finish, and the second thread will come and overwrite it with P2, which we don't want to happen. So that's why this example is not thread safe. And the reason is because when we have compound actions, imagine this is action 1 and action 2, you might get into the case where just between the actions, some other thread comes and checks this part, which shouldn't be checked, which should be done collectively with both of the operations. In this case, checking whether the name exists and setting it, you can consider one operation, although physically it's not one. That's why what you have to do is you have to lock both operations together. Okay, so that's atomic compound actions. Poll link. Oh, okay. Someone didn't access the poll. Thanks, Olden, for sharing. Okay, so how can you deal with this? Well, one thing is reverting back to using locks. Another thing is that usually these collections or packages, they have thought about this issue, and therefore they usually provide variants of their operations which are compound. In this case, load or store will do effectively this thing, but combined into a single operation, which is thread safe. And when you use load or store, not only does your code look nicer because it's more, more succinct, it's also thread safe because the package will now lock both operations together rather than locking them individually. Okay. So Amin asks, how can I get the link? So the way you get the link is slido.com and write thread safety and click this thingy and you're inside. Okay, cool. So to sum up, actions which are part of the same environment, in other words, compound actions, which should be locked together, need to be locked together. Finally, the final meaty, interesting topic for today, probably the best, keeping dessert for last. That's visibility. So imagine that we have this example of a phone book, but we don't know about sync.map, so we just use a lock. And forget this, look at this first. We use a lock and we are locking both get phone number and set phone number. So this code is fine. There's nothing wrong with it. But suddenly your boss comes and says, hey, you know what? My phone book is not performing very well. Can you do something to speed things up? So what you do is you just remove the lock on the getter. Why not? Why not do it? Because when all the examples I showed you so far just deal with, racing effectively. Some threads race to change some data, and depending on which thread does it first, you might get into a bad state. But if the threads are just reading the data, it should be fine, right? I mean, there's no need to lock it if you're just reading it. Sure, you might get some old data from time to time, but that's just something you have to live with, right? Okay, and that's the final question for today. Let's reset the results again and enable the poll. Is it thread safe? The question is this version of the code without the lock on the getter thread safe or not? Okay. Again, there is no full consensus, which is nice. I mean, I'm happy to see that there's something new you learned today. Okay, so most people answer yes. That's what I expected, and that's why I love this section, because the correct answer is that this code is not thread safe. Why isn't it thread safe? Because whenever you deal with, let me see if there's some nice tweetable thing here. Yeah, okay, this is it. Thread safety is not only about concurrent writes, it's also about reads. And in order to demonstrate that, I have this example which I can't really run, but it's still good to look at. Imagine that we have two shared variables. So these are shared by two functions which are executed in different Go routines, different processors, etc. What happens here is that one Go routine sets the number to 42 and sets ready to true. The other Go routine waits for ready to become true, and while it's waiting for it, it will just cycle forever. And once it's ready, it finishes and goes to this line and says, is number equal to 42? If it is, the run completed successfully. But if it's not 42, you get a wrong number, expected actual. So in this particular program, the result is totally unpredictable. It might run successfully, it might loop forever, so get into an infinite loop, or it might even get a wrong result. Why is that? Because whenever you have different threads executing on some data, they don't necessarily know that there are different threads mingling with your data. So what I'm trying to say is that imagine that you have a single threaded program, and your single threaded program, sets a variable to 10 and then reads it. In a normal scenario, whenever you have that, your program knows that you have set 10 beforehand, and then it's going to read it. So you're guaranteed that your value will be correct in the end. And that's something every programming language promises. If you have a single threaded application, it will appear as if it's executing sequentially. However, the key thing here is that it will be as if it executes sequentially, but that's not necessarily the case. There might be the case where it might reorder some restructure for performance sake. There might be the case where some instructions are deleted altogether, etc., etc. All these things are something which compilers do, virtual machines do, and all of them are done for some performance purposes. That's why we have all these very fast and performant compilers these days. But one thing which is preserved in the end is that your program will appear as if it's just executing line by line, but that's not the case. However, whenever you are executing your program from multiple threads and you are not kind of informing them that the program is executed by multiple threads, the compiler has no way of knowing that ready or number will be accessed from another thread. Therefore, the compiler is free to do whatever it wants to optimize this function as if it's running in a single thread and there's no other thread running you can see in it. Which means that it might, for example, go and say, oh, you are doing an infinite loop here with a variable which never changed. Let me do this nice trick where instead of checking this variable if it changed, I'll just substitute this for true instead. That's just faster. So you get an infinite loop. What will happen in that case is that if the second thread changes ready to true, well, the first thread has no way of detecting that because it's already done its optimization. So it's actually not reading a variable, it's just reading a constant true in there. That's just one example of things which can go wrong when you aren't dealing with visibility. And the way to deal with these issues is by using thread safety mechanisms, either using thread safe collections, using logs, using atomics, etc. Because whenever you are using these mechanisms, you aren't just protecting yourself from data races, like from races like the one we saw before, where depending on what gets executed first, you will see different results. Those mechanisms are protecting you from that, but they're also informing the compiler, hey, you know what? This ready variable is locked, meaning that it might be read by another thread. Therefore, you should be careful not to, do some nasty tricks in order to optimize it because the program might not be correct anymore. So that's the difference when you use thread safety mechanisms, and that's why you should be careful about those things. Okay, and that's the final thing I wanted to cover today. Let's see the questions for now. Can a channel be used here for informing the other Go routine of the change? So yes, channels, I forgot to mention them. Channels also inform the compiler that some data will be accessed by multiple threads. Therefore, yes, it achieves the same purpose. The question is whether using channels is feasible in this scenario. In this case, I think it probably is, because you might have this function, instead of changing the variables directly, push them through some channel, and then they can be read by the other functions. So yes, I think this makes sense in this case. But yeah, in a nutshell, channels also prevent this nasty issue from happening. All right, let's recap. First off, whenever you have a stateless function, it's thread safe. We saw this example with weekend safe and weekends unsafe. One of them locks the function, the other one doesn't. Despite that, both functions are thread safe because both of them are dealing with local data, which is not visible to the multiple Go routines which are doing that local data is confined to the Go routine which is accessing that function. Therefore, when you have a stateless function, it's thread safe by default. Okay, thread safety is about both reads and writes. Yeah, so in this case, whenever we have this, we saw this example with the phone book where we have a setter which is locked and a getter which is not locked. This is bad, and you can run into issues because of the visibility thing I told you about. So you should lock both the getters and the setters. When thinking about how to address a thread safety issue, prefer delegation instead of doing it yourself. So instead of locking everything yourself, try searching on the internet about some nice concurrent collection which does the thing for you, and your code is nicer and does it in a better way. Finally, be careful with compound operations. In this case, we have a synchronized collection, but whenever we have two actions which are part of the same invariant, in this case, checking whether a name exists and setting it, they should be synchronized together. Instead, prefer using something like load or store, which does that for you. But beware, when you have compound actions, the thread safe collection does not save you every time. Well, is that everything? As Alvin, asked, and I answered, no, there's some other stuff to have in mind as well, like what are what are atomic operations, how does a lock work, what's the difference, why is one better than the other, is there a different way to handle thread safety issues? Yes, there is. Where do I learn all that? First, what do you need to learn? Well, how to handle coroutines and channels. That's something which you probably can find in most concurrency in Go books. But there's some other stuff which are typically not covered as well, like what's thread confinement, what's an immutable object and how does it help? What other concurrency toolings do you have, etc., etc. So all these things are something which is just some extra topics which you need to deal with. Where do you learn about that? Well, there's this nice little book. Well, it's not little, it's kind of big, but it's pretty cool. It's actually one of the best books I've read called Java Concurrency in Practice. And this is the point where, most people in the talk are quite disappointed because it's a talk about Golang and I'm recommending Java books. Sorry about that, but unfortunately, all the Go books out there about concurrency, in my opinion, are not good enough in the sense that they don't cover everything you need to know. On the other hand, this book in particular, Java Concurrency in Practice, covers everything you need to know, and it covers it in a nice, succinct way. It doesn't go into too many details you don't know. It gives you exactly how much you need in order to be, competent on the subject, but not more, because there are some topics which you really don't need to know about. You would only need those topics if you're writing the Golang standard library. So that's why I recommend this book. It's very good. It's one of the best books overall about programming I recommend. And the concepts it covers are not only about Java, they're applicable to any programming language. So go get it. It's really nice. All right. In terms of the materials, I have this link here with the code which you can get and all the examples and things like that. bit.ly/thread-safety-go. So you can let me copy it and paste it in case you don't remember that. Okay. So thank you all for listening, watching. Thrilled to be here today. Hopefully you found you learned something useful today, and hopefully it was interesting. Enjoy the rest of your days, and yeah, if you have any questions, I'll be happy to answer.
Can I just, if anyone's got any questions, obviously feel free to stick them in the chat. But I just wanted to first and foremost thank Prez for a great talk. Obviously learned a lot. I'm sure many people did around thread safety. So just thanks so much for joining us this evening. Prez gave a great talk, and yeah, there's a lot of interaction and really like the use of polls and stuff like that. It was great. This has been recorded as well, so I know Prez has put some links. This has been recorded, we shared on our YouTube channel. I'm sure if you've got any questions, feel free to tweet Prez, add him on LinkedIn. He's happy to answer any questions you have. And obviously, yeah, thanks everyone else for joining us. We obviously run these talks on like a monthly basis, so follow Amicus Recruitment on LinkedIn and keep updated on talks, etc. But yeah, thanks so much once again, Prez. Really appreciate it.
Thanks a lot, Shaun, for inviting me.
Perfect. All right, then have a great evening, everyone. Cheers.
Cheers.
Bye-bye.
Bye, everyone.
Bye.